Okay, we're picking up from the last video, and we're going to try to do this system of differential equations from the beginning. And again, the concept here is that we believe there are two straight line solutions to this system, and we're going to find those, and then using the linearity principle, we'll make a linear combination of the two of those, and that'll give us our general solution. Okay, so finding eigenvectors and eigenvalues. Our matrix here, if I put this in matrix form, right, looks like this, where my A is 1, -1, 0, -2. Okay, so we want to find the eigenvectors and eigenvalues of this matrix. That's what in the last video we realized was the key to finding the straight line solutions. Okay, so the way it works is we subtract lambda from the main diagonal, and we take the determinant, which I've written with straight lines, but I could also put det in front. Okay, and your eigenvalues are the lambdas that are going to make this determinant 0. So when we get the determinant here, so upper left times lower right, 1 minus lambda, -2 minus lambda, minus, well, 0, the other diagonal. All right, so it's just 1 minus lambda, -2 minus lambda. Okay, and yeah, we want this to equal 0. We set it equal to 0, and we solve. Now this one is nice. It's already factored for us. Right, so we get lambda is either 1 or -2. So these are the two eigenvalues. You don't always have to get 2, but we did in this case. You'll always get, if you start with a 2 by 2 matrix, you'll always end up with a quadratic, but this one was already factored for us. But in general, you might have to use the quadratic formula or like sort of factor it yourself or something like that. So we got two real solutions. So there we go. Now each one of those then will have a corresponding eigenvector. The way that works is you go back to your matrix with the minus lambdas on the diagonal, and you put in, and I'll just do it up here, let's do the lambda equals 1 first. So we're going to do 1 minus 1, -1, 0, -2 minus 1, which simplifies to 0, -1, 0, -3. Okay, and then what you do is you look for the eigenvector is a vector that this matrix will, when multiplied against, will turn into 0, 0. In linear algebra, you call that be a vector in the kernel. So we're looking for the kernel of this vector. And this ends up just being an algebra problem. Sometimes you can see it immediately. Sometimes you can do RF, right? We can RF. We can go 0, -1, 0, -3, and then augment it with 0, 0, and we can RF that. I think in this case you can see that, for example, a 1 here and a 0 here will work, because 0 times 1 will be 0, and then if the y is 0, -1 times 0 will be 0. So I think 1, 0 will work. If you were to RF this, you would get this matrix, which would tell you 0x. The first line would say 0x plus 1y equals 0, which of course would just tell you that y equals 0, which means x could be anything, because we don't have, x kind of went away here. So yeah, so 1, 0 works. 2, 0 works, 3, 0 works, anything 0 works. And that's the way these eigenvectors work. You won't just get one necessarily, you'll get any multiples. You get all multiples of one vector. Now we only need one of them. We can just call it 1, 0. So that's the E vector, that's the eigenvector that goes with the eigenvalue of 1. Okay, now we'll do the other one as well. Lambda equals -2. All right, so I put in the -2 here for lambda, so I get 1 minus a -2. So 3, -1, 0, and 0. And again, I'm looking for a vector in the kernel. I'm looking for a vector that this matrix kind of kills off when I multiply it and gives me 0, 0. Okay. And again, I'm not going to, I showed you the RF just to remind you that you can do it that way, but I think a lot of times the easier way is to just think about it. In this case, I can see that so I just need 3x minus y to be 0. This line doesn't tell me anything because that one will always work. 0x plus 0y will always give me the other 0. So I just need 3x minus y to equal 0. I need 3x to equal y. So any vector x, y where 3 times the x will give me the y will work. So like 1 and 3, for example, works. Any multiple of that will also work. 2 and 6 will work. 1/3 and 1 will work. Anything like that. Okay, so that's the corresponding eigenvector for that guy. All right, so now we found the eigenvalues and the eigenvectors. Now we come back to the world of differential equations and we turn these into the actual solutions. So for this eigenvalue and this eigenvector, the solution would be 1, 0, e to the 1t. So the lambda goes in with the t, and that's what we talked about in the last video, that it would be an exponential with lambda, as the coefficient next to the t in the exponential. And this guy will be, so I'll call that y1. y2 will be 1, 3 e to the -2t. And you can check that both of these will work. And in fact, both of these are the straight line solutions that we looked at on the calculator. Here they are again. So yeah, the 1, 0, right? 1, 0 would be here. That was this straight line. Any multiple of that would be here. And 0, and so it stays. It's just a multiple of 1, 0 as a vector. But the e to the t part now is actually saying like how fast it goes out along that line. It's moving exponentially at a rate of e to the 1t. Right. So the multiple of 1, 0 is a function of t. So it's moving out along that line. Or if I start at 1, 3. Starts right up there at the very top and goes in, it's moving at e to the -2t, that negative exponential, right? It's going to make these get smaller and smaller and both go to 0, so that's why it's going inward. But those are the two straight line solutions. And in fact, these are the two, well, I think I did 1/3 and 1 for this vector, but that's the same, right? That's a multiple. But except for that change, these are the two solutions that I just proposed back when we first saw this example. And at the time I didn't tell you where they came from, but now you know where they came from. I wrote them as e to the t 0, and well, like I said, I had 1/3 and 1 here, but let me just go with 1 and 3. I had the exponentials inside rather than pulled to the outside of the vector, but it's the same thing. And now that means that we have the general solution. Okay, so that's the general solution. And finding C1 and C2 now to match the particular initial conditions that we happen to have, yeah, you just work that out. Let's do that real quick. So we know the answer is supposed to be 4 and 3. When we plug in a 0 for t, now these are both exponential, so that'll just give me 1. So C1, 1, 0, plus C2, 1, 3. Right, so it's just algebra. It's, 4 equals 1c1 plus c2, 1c2, or 3 equals 0 plus 3c2. So we can see that c2 has to be 1. And then if c2 is 1, I can see that c1 has to be 3. And so our final solution is y equals 1, 0, e to the t plus 3. Nope, sorry, 3 there, 1 here. 1, 3, e to the minus 2t. That's the solution in vector form. I can put it together in one big vector if I want, right? 3e to the t plus e to the minus 2t, just sort of going across the tops, or going along the bottoms. That one's 0, and in the bottom I would just get 3e to the minus 2t. That is my little x of t. That is my little y of t. Okay, so that's the idea. So you just saw a homogeneous differential equation system solved sort of from beginning to end. The only thing I'll say is that this all went well because we were able to get 2 eigenvalues and 2 eigenvectors. That is not always guaranteed, and when you don't get 2 of them, then you won't get the 2 solutions to patch together for your general solution. So something else has to be done, but we will talk about that. Okay. Let me just conclude this video anyway with a little bit of terminology, a little bit of something we've noticed. So when the eigenvalue was positive, so I pointed this out, the straight line solution along the corresponding eigenvector will go away from 0, 0. So that was like the e to the t one, right? That was the one along the x-axis that went away because it was growing. So the numbers were getting bigger, going away. And similarly, if the eigenvalue is negative, the straight line solution will go towards 0, 0. That was like the other one, the e to the minus 2t. The general solution is a combination of both of those. So if both eigenvalues are positive, then your 0, 0 will be a source. Everything will go away. The straight line solutions, if both eigenvalues are positive, both straight line solutions will go away. But then also any other one will go away too, right? Because it's not in a straight line, but you're adding together 2 things that are getting bigger and bigger. So that's going to go away from the origin. So that's what we call a source. If both eigenvalues are negative, same deal, it'll be a sink. Again, both straight line solutions go into 0, 0. But any other solution, being a linear combination of them, will go to 0 as well, just not in a straight line now. If you have one of each, which is what we actually had in our example, this is actually called a saddle. And so this is new terminology. We've had sources and sinks back in single linear differential equations. But now a saddle is when you have one positive and one negative. And so that's what we're seeing here, right? So we have along this line things go inward, and along this line things go away. And the result of that, if you start at any other point, so if I start like say here, it follows, see, it kind of follows the inward one, but it doesn't quite get to 0, 0, and eventually the other straight line solution kind of takes over and we go out that way. Let me just do it one more. If I were to start, say, let me start down here and a little bit to the left, but not quite on the line. I don't think I'm on the line there. Goes in, but then it curves out. Yeah. So we get all these like swooping lines that come in from up here and then go away out this way, or they go in this way. Let me do one more. If we started over on the other side, yeah, It starts going in this way because it's kind of close to this line that wants to go in this way, but it's not there, so it also gets peeled off and goes out the other way. So we get all these like swooping hyperbolic lines. Okay. So I'll stop this video at this point.